Today, we will talk about the problem formulation. One more thing is that for your network, so we have been experiencing strong interference among the routers, so that you may have difficulty doing git pull or other things. And the second part is the finite state machine. I believe some of you learned it from somewhere. But we will talk about it in terms of the Duckietown today. We will have a short in-class exercise, and that will be that you will draw what's your Duckietown environment for your final project, final presentation. And the second thing is to draw your finite state machine, the diagram. And the second part for today is the finite state machine tutorial by Guo. Okay, and he will talk about all the details how the finite state machine implemented in Duckietown. Okay, and the last part, we will try to do something all together. So if you haven't done the 123木头人, if your robot cannot recognize the face yet, and you will still have some time to do it. But by 5:50, we will have 10 Duckiebots, and we wish to do 123木头人 all together. And the second part is the tutorial 2. So we try to control the Duckiebot by your Jupyter notebook. And I hope that we can, each team can calibrate their robot for their turns and then do some interesting motion, for example, to overtake take a vehicle. Okay, and actually this course is called Creative Software Project, right? And so far, I think for the creative part, you guys have done a very good job in your midterm presentation. And about the software part, maybe you will expect you write lots of code in the beginning of the semester. But I think we try to use Jupyter Notebook and some tutorial and some assignment to force you guys to read the code and to write some code. Okay, then I hope you are okay with our software part so far. And I think the one very important thing is that in our midterm, we have a very ambitious goal. And I think that's a great thing. And for the final presentation, because we have limited resource, or we want to simplify the problem so that we can do something interesting in this scale of resource and time. Okay, so this is one thing, one very important part we would like to cover together, how to formulate a problem, how to make it doable in the next few weeks. And we also mentioned that actually you can try to cheat as much as possible and try to make it simple enough so that you can prove your idea. Okay, this is a very important part that for many engineering, if the whole thing is too difficult, then we should break it down and make it simpler and solve it one by one. Okay, and for the project part, this is a project-oriented class, and so far for teamwork, I think some of the team they work together pretty well, and but in most cases, maybe one person did lots of work and others may not. And probably you guys don't have lots of experience about working together with others. You guys always have to compete to get highest a score and do it by yourself, right? That's our traditional like Taiwanese style education. So You guys please also think about now who is the leader in the team and who is responsible for what. So this is also a very important part. And also if you have a team leader, maybe one of the teammates can do perception part. In our tutorial 1, it's pretty much about perception, right? And the second tutorial is pretty much about how to drive your robot. Okay, so you guys can actually work together. Someone is responsible for perception, maybe someone for motion planning, for example. And actually this is a typical assignment in a robotic team. So for example, when in the DARPA robotic challenge in MIT team, they did have 3 small teams, and each team has a leader. Okay, and they like talk a lot and try to sometimes fight with some idea to each other. But I think that's the good thing. Okay, so I hope that this is another opportunity we learn how to work together in this class. Today the focus, one focus is to simplify the problem. So I also work with our TAs, and we want to show you guys some examples. I think this is one simple setting for the parking scenario. We have 2 or 3 teams, right, doing parking. And thanks to Jake, so this is something maybe you can just make it very, very simple and try to prove your idea. So on the left-hand side, that's the setting of the environment. We actually try to draw something on the whiteboard together and think that, so now we have some weapons, we have some core functionalities. We introduce them in the tutorial, or we have done it in the assignment, right? And we can use all these functionalities to solve my own project. Okay, so you can see that on the left-hand side, the basic idea is that this is still a lane following, right? I think everyone can do it now. The parking space, there are 4 spots over here, and each one there is a airport tag, and you can see a red line over there. The only thing left is that you need the airport tag detector, which is actually provided in Duckietown repo, right? And you may want to say, this is my Duckybot, and this is my camera. Then when I see airport tag somewhere around here, maybe about just 30 centimeter away, and I will switch from lane following to a parking mode. Right? Just like you learn how to park when you learn the driving, and the coach tell you when you see something, you start to turn your wheels for 2.5 rounds, for example. Okay, and you can see that on the right-hand side, the vehicle see the airport tag and turn into this spot. And the good thing is that we have a red setting there. It's a stop line, so the car will just stop there and cover the airport tag. Okay, so that the second vehicle, when the second vehicle drives through the same parking lot, it will drive into the second spot, not the first one. So this is one of the very, very simple thing, one setting. Maybe you can just, for the parking team, you guys probably can do it. Okay, and one thing I would like to mention is that I think for the midterm, we focus about creativity, and for the final presentation, we will focus more about a software part. So that I wish that although you don't need to do exactly the same thing, maybe your midterm presentation is too ambitious. It's not very easy to get it done in 2 weeks, right? And you can simplify the situation. Okay, or even you are not doing parking during the midterm, but you want to join the competition for parking during the final. That's okay. All right. So I wish that you guys can actually try to do this problem formulation and make something to work. This is a first scenario, and we also actually. Myself and all the TAs, we sit down for more than an hour and talk about each team and try to think about how can we simplify the problem and make it doable in 2 weeks, right? And we are not going to show our discussion to you immediately. So I guess you guys may come up with even better idea to make it work and make it amazing. Okay, and this is the second one, thanks to Brian. This is probably a setting about agriculture robot. So for example, a robot want to go to a strawberry farm in 大湖草莓. And then there are like some kind of this kind of terrain, and the Duckiebot want to stay in the center lane. Okay. So this is probably about another setting that you can simplify. You don't need to go to Miaoli to do your experiment, right? It's probably lots of effort to get there. But you can come up with some setting and try to prove your idea. For example, you have IMU sensor, right? And if your Duckiebot is slightly deviate from the center, then the IMU will tell you. And you can try to control your robot and put it back. This is the second example. And this is the third one. So I probably mentioned about the factory, the shoes, 鞋带工厂 in China, right? And the test is very simple. The boss say, he just tried to put the yellow tape on the ground. And the robot can ship the shoes, can transport box from A to B. And you may find like this is probably the one thing difference is that in our Duckietown it's a more controlled environment. Everything is on the mattress, the black one, right? And your background is relatively clean, so that it might be easy to detect the white line or the yellow line very easily. Okay. But when it comes to a little bit about nature environment, so maybe the white segment is not working anymore. You may get lots of different direction or line segments. Okay, this is actually what happened. Even that this is like a regular, it's very unreliable to use white segment. So that this is Guo will actually show you guys this today. From lane following, we will switch to another state, another mode called yellow only. Okay, so that the robot can just follow this as the curve. And I think this is another great example to prove your idea that you just do something very simple. The good news is that we actually show the video to the factory manager, and he liked it a lot. And now he wants to find a manufacturer company, 量产 our stuff. Can you believe that? By this. We have a team working on finding a survivor, right? And we actually talk about the graph. We talk about the search strategy, the algorithms last week. And I think this is a perfect example for those. The thing is that we need to simplify the problem first. Otherwise, it will be very hard for us to build to crush a building, right? And build some drivable or undrivable space. And I think this is we actually just draw this on the whiteboard. And this is, I think this is a perfect example. So when can a Duckiebot determined this is a node, remember, right? A node. And this is we visited or we didn't visit it. So there are lots of things to do. Okay. And maybe this is still too hard, but I can introduce you another weapon next week thanks to Brian. Actually, Brian did this in MIT Duckietown when he was in MIT this summer. We have a Duckybot in action now, and we have a motion capturing unit. And you can see that this is the Duckybot on the bottom left. Top left, that's the Duckybot camera. And you can see that the vehicle, we can actually chase the vehicle pretty well on the map. Okay, so suppose we simplify the problem again by providing the location of the vehicle. And we can do maybe that first, because the other part of the Duckietown is a little bit far from the motion capturing unit, so that the detection become on and off, right? You guys can see it. Okay, and my point is that we can even simplify the problem by providing a location for your scenario. If you want to deliver your meal from to table ABCD, and if you know the location, that will make it very simple, right? That's more like a waypoint. You go from waypoint A and then to B to C, or you can just run through the entire graph of this map and try to search your target. Where is my survivor? And we actually also have some hardware support. Okay, we have stronger motors now. Last week, Yuri also showed us about driving the robot by the IMU on a cell phone, right? And he also get the Bluetooth part done in 2 weeks. Amazing guy. Okay, and I think you guys, if you want to use this part and extend it, we are very welcome. So far, we have been talking about lots of examples how to make your scenario easier, and one very important part would be the finite state machine. Okay, which we will cover it in a second. So after introducing finite state machine, I will leave you about maybe 20 minutes, and you can think about what kind of Duckietown environment, how to simplify your problem and make it doable. Okay, so you will probably draw something like, maybe something like this, or maybe something like this, or maybe something like this, or this, okay, for your own problem. And we will hope that you can also draw a finite state machine FSM diagram, so that, for example, I want to switch from regular lane following to yellow only. How do I switch to the other state? How do I do this transition? How do I trigger this by something, by a perception or something, by an object detector? Okay, so how many of you learned about finite state machine? Yeah, so actually finite state machine has been used in all different fields. Okay, and for example, also write the parser, or maybe to generate some alphabets. Okay, or some like regular expression. Some of them can be done in finite state machine. Okay, and also of course in the circuit and also maybe in the network. How about that? Can you name any of finite state machine in this building? Maybe just a very simple one. Light? Some light, especially in the living room maybe. Then there are maybe 5 or 6 light bulbs, right? And then if you turn it on just once and turn it or turn it back off and on, and it will switch the different way to turn on this light bulb. So here I would like to show a few examples, and one very simple one. For example, the vendor machine. So when you press those buttons, they are not going to give you anything before you put a coin in there, right? So there should be some state that will remember, okay, the state Like, have you put the coin or not? Or elevators, or okay, so let's look at a very, very simple example. It's an automatic door, maybe just in this building. So you can see that there is a door over here, and front and rear, okay? And I just try to cover this again. It's in a textbook theory, this textbook. So for the door, we actually have two states. One is closed, the other one is opened. Okay, and we are just trying to make a little bit like formal definition of this. So maybe you guys learned it maybe with a different expression or different express this by different symbol, but that should be something similar. Okay, so you can see that this is a finite state machine over here, and we have two states, the closed and open. Okay, and there are a few conditions that will make the door open or not. Okay, and you can see this is the state here, and we have a few input signals here. Both the state and input signal, they become the transition function. Okay, so let's make it a little bit formal over here. Okay, so we have a finite set of Q, we call it states, and we have a sigma, like we call it the alphabet. So this is more about the, for example, the input signal in previous example. And one thing very important is the transition function. Okay, so when you are at a state maybe A, and some event just come in, and that trigger it to go to state B, for example. Okay, and in some scenario, there is a state, and some scenario there is a set or maybe final state. Okay, so in some situation, the state, it cannot stop at somewhere. So this is another example. We have Q1, Q2, and Q3, three states over here. And we have the alphabet. It's more like the event we are going to talk about in our Duckietown. So by the states and by the alphabet or events, we can have a transition function over here. Okay, so you can see that Q1 is not going to move to Q3 directly, for example. So we will have to see what's the right transition between those the states. Let's use the same symbols for now. And maybe some of you can, if you know Duckietown well enough, how do we use the finite state machine in a Duckietown? What are the states in Duckietown? So we talk about lane following, right? That's one of the states. How about anything else? Actually, joystick is another state. How about the alphabet? Actually, the alphabets here, they are more like the events that will trigger state come from maybe something, maybe from joystick to lane following or something else, some other state. So is there any events you know over here? Detect a phase. That's great, that's great. Okay. And actually, I can show you this for the events, the alphabets. So they are pretty much, lots of them are perception-based events. Okay, so for example, there is a red line over here, and the ducky bar will stop. Okay, so switch from lane following to another state. Okay, and for example, in our example, so whenever you detect a phase, that could be a trigger. That could be an event to transition from maybe lane following to something else. So you definitely want to avoid a pedestrian, right? So instead of just run over it. Okay, so let me show you the FSM in Duckietown. So we actually start from here. So when you guys do step H, right? So when you run the lamp following launch, so you will actually get started from here and then go to joystick control. We actually, how did we switch from joystick to lamp following? Do you guys remember the command, how to switch from joystick to lamp following? Cross service call, there is a command called set state to lamp following, right? Yeah, so that's one way to set the state from joystick control to lamp following. But some of the state could be triggered by perception. Okay, so for example, if we look at this diagram, and there is a state called avoid a vehicle, and you can see that this is a vehicle detected, okay, and vehicle clear over here. And also there is another state called coordination. So that usually happen when the Duckietown is in an intersection. Okay, so this is another perception-based event at stop line. Okay, and then the state will transition from lamp following to coordination. And actually coordination will move to something else very quickly. This is some example of a finite state machine in Duckietown. And the other important thing is that although we open multiple nodes when you run lamp following dot launch, but only one node get to control it in one state. Okay, so for example, when you are in joystick control state, the switch will go to, it's called car command. When you switch to lamp following node, your joystick is not going to control the robot, okay, because the switch, there is a mechanism to switch among different nodes, okay. So it's not always safe to send the car command directly to the Duckiebot. They may interfere each other. Okay, so that this is one node actually in Dagu car in that module, and there is a node called car command switch node, and this car command switch node will try to determine what is your current state, and it will only accept the car command from that state, node. Okay, but remember that, for example, in the then following launch, all other nodes are still running. Okay, they just don't, the switch just don't accept its car command. Okay, so you can easily switch between different behaviors.